Okay, guys. With this reaction here, we saw a very important concept that we're going to see a good bit going forward. That is resonance. When we reacted here with the H+, yeah, and we made cation, boom, 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 boom. We made carbocation here. We should be able to predict that based on what we've done from day one with alkene reactions, secondary versus primary. But more importantly, this cation is said to be resonance stabilized. We showed this last time. We should have this. Resonance stabilized. These electrons next door can move in. At least on the board we move them in. Resonance arrow. Double-headed resonance arrow, and we get boom, 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 boom. Double bond to the chlorine. 2 lone pairs left. Positive charge now on chlorine. And the new H is still there. This is a resonance structure. All we moved is pi electrons. This kind of looks like back bonding, but when we do back bonding before, we made sigma bonds. This is pi bond here. These are really resonance. Whenever we do resonance, these 2 structures are really, they're fake. First off, this here in the circle, this is one cation. It's one compound. It's one intermediate. It's one everything. I got 2 structures shown on the board, but it ain't 2 structures. We're going to cover resonance when we get to test 3. But it's important to start thinking about it, so I want to explain a little bit more here. The true structure is in between here. That is, if you had a cation here, and electrons next door, would these electrons be attracted to the plus charge? Or would they be like, just ignore it? No, physics tells us there will be some attraction here. Well, how much attraction? Will these electrons move in here and exist in here as a second bond? Well, bonding is good. But hold on, chlorine's a little greedy. Does it want to give up the electrons and become positive? No. It sits in between. In between is boom, 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 boom. Maybe instead of a full second bond, it makes another half a bond. And if it makes a half a bond, the chlorine is only partial positive. And if we make full bond, this becomes neutral. But if we make half a bond, it becomes only partial positive. It's halfway to neutral. This is the true structure, closer to the true structure. This is called a resonance hybrid. True structure. Resonance hybrids, though, show partial bonds, and partial bonds can be cumbersome to draw. So instead of drawing this, organic chemists instead stick with discrete structures without partial bonding. And just so to say, the true structure is in between. This is the idea of resonance. Then when the other chlorine came in, importantly, even though these are fake, you can work with either one of them. The chlorine comes in and attacks this partial plus and kicks whatever bonds are here, whatever electrons are here, pushes them back up to give this product. Work with either fake resonance structure. We could either bond here, that gives this, right? 2 chlorines on the same carbon. We can also work over here. And the only thing new, we did this last time. You can also work here. These electrons add here and push these back up. That electron movement also gives this. By the way, you still need work on mechanisms, guys. looking at the bromination lab, BR2. It's barely even half complete mechanism for that. And that's homework essentially, and it's right out of the textbook, so I'm not quite getting it. But need a lot of work on your mechanisms. There'll be 2, if not 3 mechanism questions on the test, worth about 25 points. Okay? Doing mechanisms is a huge part of organic chemistry. Maybe some of you don't realize that you got to know mechanism, more than just predicting a product. And understanding, a lot of you are missing arrows, using arrows backwards, etc. You got to know what this means. This is making a bond here. What does this mean? These 2 electrons are moving back up here and becoming a 3rd lone pair. And that gives this. Okay, that's resonance. Very important. Let's move ahead. Any questions? We did make a vinyl cation over here. Vinyl is an alkene cation. Because our first cation here, when we came from here, the cation was on an alkene, if you look at it. Okay? I'm not going to say much about it. Those vinyl cations are pretty bad, but they can be formed. We're not going to look at the stability of those versus primary, secondary, tertiary, but I tell you they're worse. Thus, this tends to be a slower reaction. I'm not going to say anything else about that. Vinyl is just a slang name for alkene. B, we pretty much answered when looking at the reaction. We get a geminal dihalide. Chlorine's on the same carbon because from here the cation forms again here. And if the cation forms again here, the chlorine's going to end up here. So it's going to be geminal. The next cation does not form out here. So we pretty much have already explained this. That's just sort of written out. Let's look down here. Reaction with elemental bromine or chlorine. First reaction with bromine will give the trans addition of the 2 bromines across the pi bond. Anti-addition, because the bromines are anti, it will be E, not Z. High priority groups are on opposite sides. That should make sense. Bromonium ion, backside attack, you should get this. Open it up. But the alkene is still here. We have an alkene left. We can react again. And we can add bromine across the second pi bond and end up with a tetrahalide. In this sequence, we have stereochemistry here about the alkene. There's no stereochemistry. There's no alkene and there's no chiral carbon. So you can draw that however you want, as long as you have 2 bromines on the first carbon and 2 bromines on the second carbon. But you should understand why this stereochemistry is here, because of the bromonium ion and backside attack. Okay, now let's look at addition of water to alkynes. When we add water to alkynes, first off, you only do it once. Okay? In those previous reactions, we did it twice. You only add water once. Forget about reagents, but if you add water across the pi bond, you're going to get such a product here. Okay? 1 H on the N carbon, now 2 H's on the N carbon. So we've added an H here and an OH here. That's water. This guy has a name. It's called an enol. An enol is an alkene with an alcohol on the alkene carbon. So the ene comes from the alkene, and the OL comes from the fact that it's an alcohol. You have the OL ending. Enol. And you kind of remember that's like what a donkey sounds like. Enol. You ever heard a donkey say Enol? He's talking about enols. Okay? Enols are not stable. Usually not. We're getting two. I'll show you a couple if you have me that are stable. Sometimes they're stable for various reasons. If you have an argument and a reason for why they might be. In general, they're not. Brackets around something means it's not isolated. It may be formed, but mechanistically it just keeps going. You can't isolate enols. After you've hydrated once, it will then undergo a rearrangement. A rearrangement called tautomerization. Formula. Here's a formula. To get to here, we add H2O to our formula. But these have the same exact formula because it's just a rearrangement. Okay? Tautomerization. Now, hydration can be done just using aqueous acid, like you hydrated bromine, using just aqueous sulfuric acid. With alkynes, which are more sluggish to react because of the vinyl cation that has to form, and vinyl cations are not great. They're slower. Historically, mercury has also been included. Mercury ion, mercury acetate, or other things, mercury sulfate. And with the mercury, this may be the electrophile, and you may get back bonding to make a mercuronium ion. And you should be able to show that, right? And then water attacks. Okay? If there was a mercuronium ion here, which carbon would the water attack? Right or left? Attack the left, the more substituted one. Okay? Also with the mercury, you don't need sodium borohydride to remove the mercury. In the end, you can just ignore the mercury and just do it as aqueous acid. But guess what? Anytime you hydrate an alkyne, you'll probably also always see mercury included with it. But guess what? We're going to do a reaction in lab. We're going to hydrate an alkyne in lab. We ain't going to use mercury. You just do it like this. Proton acid. Okay? Attack proton, we're going to leave cation here. There's no back bonding. Water attacks cation. Okay? Let's go ahead and just do it without the mercury. Again, just ignore the mercury, but you will always see it. Let's keep it simple. We got H plus in water. This is going to attack the H plus, leave cation on the left, correct? Boom, boom. All right, now we got to make track. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Boom. There's now 2 H's on the end, correct? So this is adding 1 to the end, leaving cation here. Cation here. Now we're going to have water attack. Bam. Vinyl cation. Okay, an alkene cation. It's called a vinyl cation. Water attacks. Boom, 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 boom. H, H. Now, water is now bonded here. Among a variety of problems I see with mechanisms is many of you are showing this here reasonably, or maybe not, but when you do show this correctly, what does this mean? This lone pair is making a bond here. But then for some reason, you guys are showing 2 lone pairs on the oxygen over here. If one lone pair is making a bond, how is there two remaining? There ain't. There's only one remaining, because the other one is now a bonding pair. And now this is a charge, because on day one we talked about typical oxygen, 2 bonds, 2 lone pairs. That ain't a typical oxygen, so it's likely charged. Positive charge. And hopefully, for some of you, that's just kind of second nature now. That's a positive charged oxygen. So, how do we get to the final enol? This is a protonated enol, so we have to lose the proton. What can take the proton? Well, there's got to be a minus here. I mean, there's no such thing as just H3O+. There's got to be a minus with it. Maybe it's sulfuric acid, or you can just use water. Use water as the base, and these electrons take the H, these electrons stay behind, and we get that plus what? We reform H3O+. So we reformed acid, we reformed catalyst. So there's your enol, right? A good old hydration of an alkyne. The enol is not stable. It tautomerizes to this. We already know it has the same formula. But it's a ketone in this case. It tautomerizes to a carbonyl compound. Okay? It will be ketones, but it can also be aldehydes. I mean, you all know that. If this was an H, then it's an aldehyde. But that's a ketone. And the reaction keeps going. So what's the mechanism in going from your enol to your ketone in this reaction? You already know the mechanism pretty much. Did someone say something?
Is it a hydride shift?
Hydride shift?
Yeah.
No, it's not a hydride shift. But it sounds like you're looking, what's going on here? Okay, we're going from here to here. What has to happen? Well, this H has to be, you have to lose an H from oxygen. Anybody agree? Yes. But we don't just lose H because we got the same formula. It's a rearrangement. We lose an H from here, but where do we gain an H? There's 2 on the end here. How many on the end there now? Okay, ultimately, we know that one H is sort of relocated from the oxygen to that carbon. Has anything else changed in going from here to here? What else has changed? The pi bond is sort of shifted because here it's between carbons, here it's between C and O. Well, we just came up with a definition for tautomers. And by the way, the process is called tautomerization. The two, relative to each other, they're called tautomers of each other. Okay? Should be written up there. Tautomers. What's the definition of tautomers? 2 constitutional isomers, same formula, different connectivity. 2 constitutional isomers that only differ by what? Relocation of a single hydrogen. Relocation of one hydrogen and at least one what? At least one pi bond. It could be multiple pi bonds. But it ain't multiple hydrogens. Relocation of one hydrogen and then relocation of one or more pi bonds. And going from here to here, have we relocated one H and at least one pi bond? Only one H? Or have we relocated 2 or 3 H's? Only one, if you look at it. Thus, these are tautomers. Like we said at the beginning. You got to know definition of tautomers. Like cousins. You know definition of cousins? It's like that. It's a relative comparison of 2 things. And now we can talk about it. All right, mechanism. Well, we still have H plus. This is all the same reaction class. Okay? This is formed, but there's still H plus in it. Okay. What chemistry do you know in going from here to here? I could have given you this mechanism 2 weeks ago, and you could reasonably have done it. What's the first step? What chemistry do you know here? This could react with H plus alpha. Alkyne, have you ever seen an alkene react with H plus? Mm-hmm. We've done it for 2 or 3 weeks. Yes. Where are we going to leave cation at? Left or right? Left. On the left. Correct. This attacks here. Boom, 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 boom. Cation here. Everybody liking it so far? Seems reasonable? Hold on, by the way, where do we need to put an H at? There's 2 here and there's 3 there. We need to put an H on the N carbon? Well, there it is. We just did it. The N carbon now has an extra H. Bam. Okay. What can we do next? Electrons on oxygen? Physics tells us that these electrons will be attracted to the positive. Have we ever did something like this? You want to do this? What are we doing here on the board? This is called resonance. We just did it with the chlorine in the previous example. Let's do some resonance. Boom, 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 boom. Double bond to oxygen. H there. How many lone pairs left on the oxygen? 1 lone pair left, because the other one just made a bond here. Positive charge now. Yes, it is. New H on the end. That's resonance. Just like we did with the chlorine in the previous example. And by the way, we didn't talk about resonance. We didn't talk about this part of resonance. The one reason resonance is so good is it supplies additional bonding to the cation, but it also delocalizes the charge. Here the charge is on carbon, but now we're showing that some of the charge is on oxygen. How can we get home now? Are we close? This H looks funny, right? But it's there. The new H is on the end. So ignore that. There it is. What do we need to do? We need to get rid of this H. Well, the H plus is catalyst. It's catalyst all the way through here. We've got to reform it. Let's use water. Take the H. These electrons stay behind. A lot of you are not showing this needed arrow here. And that gives what? That gives this. 2 lone pairs now, plus what? H2O plus reformed. This is acid and water. This is acid and water. We got water around. I mean, right here it tells us that this is aqueous acid. There's water around. And like you learned in Gen Chem, H plus is really not real. H plus sits with something. It never sits by itself. In aqueous acid, water is holding the H plus, right? But we use H plus as if it's a discrete. How about that mechanism? Was it consistent with a lot of things we've seen before? But we got resonance here. How many intermediates in this mechanism? How many intermediates in this mechanism? 2. We went from here to here to here to here, right? How many intermediates? I hear 1. Anybody else? If you did a reaction coordinate diagram of the tautomerization mechanism, how many intermediates would you have? Why one?
Because the two formed are resonance.
Yes, very important. This is one. This is one. That's one intermediate. When we show resonance on the board, this is just us showing two different forms of one thing. The one thing is a hybrid. This is a lot like colors. If you mix red and white, what do you get? Pink. Okay? I'm telling you that once this prognates, it becomes pink. But pink is hard to draw. It's a hybrid with partial bonds. So instead, I'm going to draw red and white and ask you to understand and know that it's really a blend of these two. Really a blend of red and white. What we really have here is something that's pink. It's just hard to draw the pink. There's only one color here, it's pink. Well, then why are you showing me red and white? Because I'm trying to tell you that the real single color is hard to draw, so I'm showing you two fake colors, two maybe composite colors that go into forming the structure. This is resonance. So when you're reading about resonance, again, because I know you already have, okay? So, there is a little mnemonic that helped remember your tautomerization mechanism. Which, by the way, anytime you do a tautomerization, same mechanism. Although, hold on, we're under acid catalyst. You can also do tautomerization with base catalyst. But there is a little mnemonic. I don't know who made it up. Some crazy person. Called Oreo. Like Oreo cookie? For remembering this mechanism. What did we do first? We put a proton on. H plus on. Everybody agree? Here it is. We just put it on. What did we do next on the board?
Resonance.
We did resonance. Why do I keep saying on the board, on the paper? Because in the flask, ain't nobody doing resonance. As soon as the proton goes on, it forms this pink thing. It's only us on the board doing this resonance. Resonance is not a step in chemistry life. It's a step on our paper or our board. Proton on. Then we do resonance on the board. On, resonance. Then what do we do here? We took that proton off. We put one on here and took one off there. On, resonance, off. On, resonance, off. That's what we just did. Now, under basic conditions, you do just the opposite. Because bases, what do they do in terms of protons? Do they put them on or take them off? See, acids, you put protons on. But if this was a base, you'd be doing what first? Yeah, you just reverse steps. If it was base, it would be off, resonance, on. Oreo works with any tautomerization today, or when you take chemistry 5938 advanced, double advanced organic chemistry, it still works then. Because tautomerization is always the same. You relocate one H and the pi bond. The pi bond, though, gets relocated when you do resonance. Well, actually not. It's sort of all the way through there. Okay, that was Oreo down below. Let's see what else we have. Which of the following are tautomers of the compounds shown in the box? Label either as an OH tautomer or a CH tautomer. Go back up to the top. We could call those other names. Two are tautomers, as mentioned, the enol and the keto form. A lot of times called the keto form. That's how it's discussed up there. Enol form, keto form. Or somebody may say carbonyl form. Okay? But we can also look at this. This would be called an OH tautomer, where this would be called the CH tautomer. Let's just tell you where the H is located. In this tautomer, the H that gets located, see if I had a red pen, I'd put that H in red or blue. That's the H that gets moved when we do a tautomerization. If it's on the O, we call it OH tautomer. If it's on the C, we call it a CH tautomer. Can we go with that? So, which of the following are tautomers of the one in the box? Okay, I want you to do these on your own because we need to move ahead a little bit and give you a little bit of time to think about them. Are the following tautomers? Are these tautomers? Tautomers are can more broadly be called what? Enantiomers, diastereomers, resonance structures, or constitutional isomers? Think about it. We can also hydrate a pi bond using hydroboration oxidation. This would give this enol, and then it would undergo tautomerization to give what? Well, does this product make sense? Let's see. Pi bond attacks the electrophilic boron. Where are we going to leave cation at, right or left?
Left.
BH3 is now a minus. Okay, this is now, I'm drawing it bent now, but the alkyne would attack, leaving cation on the left. Correct?
Mm-hmm.
Yes. But this is not actually formed because we know that this hydride shift comes in here, right? And we get boom, boom, boom. BH2 and H, right? But these are going to be cis, right? Same side? Because if the boron is this way, see this H, that's now trigonal planar. sp2 trigonal planar. So we got some projection here. If this comes in here, okay? So these two would be, well, those two are cis. In terms of overall, this thing is E, correct?
Yes.
Because that's high priority here, that's high priority here. But if you focus on these two, these are cis, right? It's a syn addition of BH3 with this regiochemistry because cation would be here. Magic step, what does it do? Same as before, replace that with OH. And what is that? Same thing I got drawn there. Everybody see it? So, there's your mechanism. I'm just going to go back and change it to BH2. Right? And we get this by magic. What is this though? It's an enol. See that enol? Alkyne with an OH. What do enols do? They tautomerize to what type of structure? Carbonyl. Okay. When this tautomerizes, what is it going to be? Please show structure. It looks like there's a question answer up there. We should start with filling in those, okay, those things next time. Then we'll be looking at reduction of alkynes. using either hydrogenation, poison catalyst. We'll also be doing on the next page our first radical reaction. First radical reaction. Then we'll finish up this looking at acid-base chemistry of alkynes. Remember the SPCH? The SPCH has some acidity because of the hybridization effect. We're here on Wednesday, right?
Yeah.
Okay, Wednesday we'll talk about things. We're off on no lab this week, right? And no lecture on Friday, yes. The following week, most likely when you come to lab. The following week we'll talk about it on Wednesday.